right, here we have a table dealing with the peasant and the king. So there's a fable about a princess being rescued by a peasant. Her father was so grateful he offered a reward in which he would pay the peasant $1, then double the amount every day for a month. I'm talking about 30 days. Well, the queen is very good at math and tells him that he's an idiot and that he's going to give away all their money. So the king comes up with this new plan where he starts with $20. It seems better because it starts with more money. He gives him $5 additional every day. So now I'm doing this a little bit out of order. First, I think let's just complete the table with the pattern. Okay, and then we're going to use our formulas later to justify our pattern. So if you're doubling, 16 doubles to 32, 32 doubles to 64, 64 doubles to 128, 128 doubles to 256, 256 doubles to 512. You can see how it grows kind of quickly. Whereas when you just add 5, 45, 50, 55, 60, 65, it's only growing by 5, it's not growing super fast. So we will use our formulas later to justify and make sure that we did this correctly or that our formulas work for day 9. Okay, so first of all, the original plan is what kind of growth pattern? Well, it doubles. And if you're doubling, remember we have a growth factor then of 2, this is exponential. The new improved plan, you add 5. If you're adding, that is linear growth, right? Where the add 5, that would be your slope because that's the reoccurring change. So let's find the mathematical model for the original plan. Well, we started in the original plan with $1. Then it doubled. Right? So if it doubles, that means our growth factor is 2. So our formula, y equals initial amount times the growth factor raised to the time period. In this case, we're talking about days, right? But here is my model for the original plan. Now, the new improved plan, we add 5 every time, which means that's our slope, and we start with 20, so there's our y-intercept. So y equals slope times x plus 20, and there's our linear model. Now, I do want to use the equations from 3 and 4. So our original 1 times 2 to the x, and then y equals 5x plus 20 for day 9. Let's just check this out for day 9. So if I plug in 9 for x, 2 to the 9th power gives me 512. Which is exactly what our table said. And if I plug in 9 over here, 5 times 9 is 45. 45 plus 20 is 65, which again is exactly what our table said. So sometimes if you know what an answer is and you're writing a formula, sometimes it's good to like plug things in to see if you get the same answer, because if you don't, there's a mistake somewhere. Whether that was when we doubled in the table or when we used our formula, created our formula, something is an issue, right? Okay, now 1 through 5. We're going to do 1 through 5 and 6 through 9. So I want to go back to the table. If you look at 1 through 5, well, what can you say about 1 through 5? Well, the new and improved plan is greater for all of those. So if this peasant is getting on a boat in 5 days and he's only going to be around for a few days, he should take the new and improved plan because it's going to be better for him in that short term. But you can see if you turn around for 6 through 9, the original plan is not just greater, it's significantly greater. Day 9, $500 compared to $65. Are you kidding me right now? Right, $500, I can buy multiple pair of shoes, whereas 65, I can buy 1 pair of shoes. Very, very different. And then you can imagine it just continues to get more and more and more. I mean, let's talk about day 20 just real quick like. If you're using your formula and you put in a 20, we end up with 1048576. That's over $1 million in the original plan. Whereas if you go 5 times 20 plus 20, 5 times 20 is 100. You're going to be up to $120. This is why the queen said, yo, idiot, you're giving away all of our money. There's 10 more days after day 20, according to, the original dealio. So it would get up into the way big millions. So in terms of what general conclusions can you make about comparing these linear and exponential models? Well, in the short term, linear might be better, but because exponentials, they grow so much faster that when you look down the road, exponentials are going to be better in this particular case. So exponentials just grow faster, which is why they're called exponentials, right? Repeated multiplication.